Hi, my name is Dr. Patty Christie, and I'm going to give you a video explanation of a second question from Exam 3 from Spring 2013 from the 511-1 class. The second question is also on acid-base chemistry, and it is question number 8. Question number 8 says, the Ka for aspirin is 3.98 times 10 to the minus 4. Question A. What is the ratio of the protonated to unprotonated forms of aspirin in the stomach where the pH is equal to 2.00? And you can assume that all the hydronium and or all of the hydroxide at equilibrium satisfies the 5% rule without checking. We are looking at the ratio of protonated HA to deprotonated A- of the aspirin. If we have both HA and A- present in our solution, what type of problem do we have? We have a buffer problem. And when we have a buffer problem, what do we use to solve that problem? We use the Henderson-Hasselbalch equation. So pH equals pKa minus log of HA over A. So here's our Henderson-Hasselbalch equation. We don't have the pKa. We are given the Ka in the problem statement. So the relationship between Ka and pKa is the pKa is equal to the negative log of the Ka. So we can do the algebra to figure out that the pKa is equal to 3.400. We are also told in the problem that the pH is equal to 2. So we have a pH, we have a pKa, and now we can do a substitution to calculate the ratio. So now we have some algebra. We have our pH equals pKa minus log of HA over A. Substituting the pH and the pKa, we can do some rearrangement. So we have that negative 1.4 equals negative log of HA to A. And now we can say 10 to the 1.400 is equal to the ratio of the HA to the A. If we do the math, we get a ratio of HA to A to be 25.1188. And with our friend 3 sig figs, our ratio is 25:1. Question asks, what is the ratio of the protonated and unprotonated forms of aspirin in the stomach where the pH equals 2.00? So the ratio of the protonated HA to unprotonated A- is 25.1. So part B says, supposing that aspirin is active only in its protonated form, is it more active in the stomach or in the blood, where the pH is 7.4? Briefly explain your answer for full credit. So this is another application of the Henderson-Hasselbalch equation. pH equals pKa minus log of HA over A. We can do the same algebra as for part A to get the ratio of HA protonated form and A- the deprotonated form. pH equals pKa minus log of HA over A. But our pH now is 7.4. The pKa is still 3.4. We can do some rearrangement, and now we can take the log 10 to the minus 0.4 is equal to HA over A-. Now our ratio of HA to A- is 1 times 10 to the minus 4. Since the ratio in the stomach of HA to A- was 25, and the ratio in the blood of HA to A- is 1 times 10 to the minus 4, and with the active form being the protonated form, then it is more active in the stomach than in the blood, because the ratio of HA to A is larger in the stomach at pH 2 than in the blood at pH 7.4. Now there's another way to look at this problem, and that is to think about the chemistry. So we have an HA plus H2O is in equilibrium with A- plus H3O+. If you are above the pKa, then you have more products than reactants, which means you have more of the deprotonated form of the acid than the protonated form at pH 7.4. So this means that there is more active form at the lower pH, the stomach, than at the higher pH, the blood. And just if you're keeping track, the math proved this on the previous slide, and so the idea is that you can either show this using math or using chemistry, whichever you prefer. So this concludes our explanation of question number 8 on our exam number 3 from last year.